Hey guys, what up, and this is Salihin. For this video, I will be mentoring on chapter 2 of Material and Energy Balance paper, which title Material Balances. I will use this textbook which title Elementary Principle of Chemical Processes by Richard Felder. And there's a lot of items in this book, but we'll go through a few topics. So for material balance, we first cover chapter 4, which terms fundamentals of material balances. And for this topic, we will cover 4.3 material balances, balance calculation, 4.4 balances on multiple unit processes, 4.5 recycles and bypass, 4.7 balances on reactive processes, and lastly combustion reaction. These all 5 subtitles is available in your lesson plan, so you can review it after every classes or after every lecture for your preferences. And let's have a look at the lecture notes. The lecture notes is available for every topics, and I usually put it in e-learning, but mostly I'll be using Dropbox because the ease of use. For anyone who want to use Dropbox, go to www.dropbox.com and you can register it for free. And I will link this folder of this paper to you, and you can access all materials I've uploaded in the Dropbox system. And you can check the e-learning websites sometimes, but I rarely use it, but I just upload it when I need it. And for this lecture notes, is good for guidance, but please use the textbook for study because all the examples and there's a lot of examples in there. Alright, let's have a look at the lecture notes, and let's have a look first. So the outline is still the same. There's 5 points, same as the textbook, and this follows the student notes, not student notes, the study guide too. And yeah, there's all 5 available in here. And yeah, I think let's start a bit on the content of this material balance. And let's go down. Yeah, for start, general balance equation is all about the equation. Yeah, it's not all about the base. It's all about the equation. So there's 2 type of balances, differential and integral balances. And for differential is usually applied to continuous process. See that, continuous process. And the integral balances usually applied for batch process. Well, continuous is like what it says, it's continuous, which means if it flows like continuously. So there's no batch. Let's say how many liters per hour, so that is continuous process, while a batch is like they put a batch like 100 liters, while continuous is 100 liters per hour. So that's the difference, and you have to determine this first to put into the flow chart or flow rate things later. I'll guide you through it. And let's look at the next slide. Bam, the general balance equation. So that's the general balance equation. All what I understand is the general balance equation. So for this is we have input plus generation minus output minus consumption equal to accumulation, which is the build up within the system. Well, input is what goes in, generation what's produced, well, you put something to produce something, and then the output is what leaves the system, either the generated product or the input product or both of them. And also minus the consumption, which what's consumed from the reaction, such as if it's combustion, the is consumed and produce something else, and the accumulation is the build up within the system, which is what's in the system and doesn't goes out. Yep. And so we discuss continuous and batch process. So continuous is input plus generation equal to output plus consumption. Because it is continuous, they just put input. For batch process, they have an initial input, which is you put something in bulk in it and you don't add up anything else, and the final output is what comes out. There's no continuously comes out. Yeah, so yeah, basically that's it, and we go to the next slide. Now let's look at the two important things that needed to be done to solve a mass balance equation. The first is flowchart, and second is the basis of calculation. Well, the flowchart is to draw a flowchart of the process of a process, which, well, it's easy for us to look on the system where it comes from, where it goes, and what's happening in the system. And the general rules is to first write the values and units of all known stream variable on the chart, and then assign an algebraic symbols to unknown system variable with their unit on the chart. And we can have a look in our textbooks. Let's have a look here. And yeah, this is on page 96 on the textbook, and yeah, it says flowcharts. Well, and for this one, oops, too much. Where is it? I lost it. Yeah, here. And so this is the general flowchart. Yep. So and so what goes in and what goes out, and the what they call it, algebraic symbol, which is this is mole. So the basis of the calculation basis is mole. If it's so, this is a batch process. So if it's a continuous process, this might be mole per second or mole per hour or liter per hour. If this is a batch, and this can be mole, liter, kilogram, and whatsoever. And for basis of calculation, let's go back to our lecture notes. Go. Go. And basis of calculation is an amount, mass or mole or flow rate, like what I said before. So if a stream amount or flow rate is given, it is usually being used as basis of calculation. So you have to set the basis of calculation. If not, you'll jumble up and get confused and, I don't know, fail the paper. I don't know, I'm just saying. So if no stream amounts or flow rates are known, assume one, preferably that of a stream with known composition. So let's go back to the example. So if there's no value here, this you have no idea what is 100 or what is whatsoever, but in the end you get the product is you get in mole of H2O, which is water. So you can assume it to be the basis is mole. If you use kilogram, yeah, you can have it in mole, you can use it too, but you have to convert it everything, and that's hard. You don't have to do this in university. That's probably in final exam a bit. Yeah, but first thing first, set the basis of calculation in your flowchart. Yep. So to the next point. Alright, now I'll show you on how to draw a flowchart and based on the question given. So the question is, an aqueous solution of sodium hydroxide contains 20% of sodium hydroxide by mass. It is desired to produce an 8% sodium hydroxide solution by diluting a stream of the 20% solution with a stream of pure water. So now the input is 20% of sodium hydroxide solution, and they want to dilute it to 8% by diluting it in a stream of pure water. So the input is sodium hydroxide and the water, and the output is the 8% sodium hydroxide. So to draw what they call it, the flowchart at first, well, I don't know how they do it, but I draw a box, and what comes in, so there's 2 comes in, and there's a product comes out. Yep, so far so good. And the aqueous solution of sodium hydroxide contains 20% of sodium hydroxide by mass. So we can put it here. 20% is, we can write it 0.20 kg NaOH per kg. While what's the other 80% is water, 0.80 kg, H2O per kg. So what comes in is also water, so we can put it M1, which is in kilogram of H2O. Since water is pure, so we don't need this. Yeah, you can write it 1.00 kg H2O per kg, just to be safe. And then what comes out is 8% sodium hydroxide. So you can write here is 0.08 NaOH per kg, and 92% 0.92 kg H2O per kg. So for what they call it, the basis of calculation, since it is by mass, you can use it by mass. So the basis of calculation is kg, but this question doesn't give how many kg, so we just assume 100 kg just to balance the equation. So what comes in is 100 kg of 20% sodium hydroxide, and to balance the equation we can put it M2, which is also in kg. So yeah, so that's how you write a basic flowchart. So all the information is here. On the M2, what comes out on the input, which is M1, we don't know how many H2O, and we don't know how many 8% sodium hydroxide available, but with the basis of 100 kilogram, if the equation gives a 1000 kilogram, then you can use it a 1000 kilogram, but in this situation just assume 1 kg, 10 kg, or 100 kg, what's possible. Alright, so I guess that's for this equation, for this whatever question is it. All right, thank you. All right, now let's try to solve this equation. And since this is a matter of balance, we'll solve it through 8. So in matter of balance, yep, and so in the equation they have sodium hydroxide and water. So we can use, I think, 3 balances, which is the first is sodium hydroxide balance and H2O balance, and the last one is the total mass balance. Yep. So let's do the sodium hydroxide balance. So as we studied before, for sodium hydroxide is what comes in and what comes out. So let's write it first. So the input equal the output. Yep. And so what's the input of sodium hydroxide? So there's 2 input here, but for this part is pure water, so there's no sodium hydroxide. So the input is only on this side, which is what goes in. Since we use the 100 kilogram basis, so we use 100 kilogram, and in this 100 kilogram there's only 20% of sodium hydroxide. So what goes in is 100 kg times 0.2 kg. So because there's only 20%, so that's the amount of sodium hydroxides that goes in. And what's come out is, since there's no accumulation of sodium hydroxide in here, so all sodium hydroxide goes out. So since we don't know M2, but still we can use it. So M2 times 0.08. So since this equation is balanced, so we can find the M2, the value of M2. So M2 is 100 times 0.2 divided by 0.08. And from here we can find that M2 is equal to 250 kilogram of sodium. So N2 is 250 kilogram of M2. So the total mass here is 250 kilogram. Alright. So the M2 is not the sodium hydroxide, but the M2 is the total amount, which is the total mass balance. So we can use the total mass balance equation here. Mass balance. Sorry if my writing is bad. And the total mass balance is the amount of that goes in is equal to the amount that goes out, because there's no accumulation in here. So since 100 kilogram plus M1 equal to M2, which is M2 is 250 kilograms. So in the end, M1 is 250 minus 100 kilogram, which in returns equal to 150 kilograms. So for M1, there's 150 kilograms of water is added to 100 kilogram of 20% sodium hydroxide to make a 8% sodium hydroxide solution. So that's how you solve a simple mass balance equation. So from there you can, if you want to use an H2O balance find to find how many H2O required available in the system, you can use it and check it to just to double check if the mass balance equation is wrong or right. So but in this situation is already right. Yeah, and if it's wrong, then correct me. All right, thank you. Now let's have a look at degree of freedom analysis. So over the time, the equation and the flow charts or flow rates get more complicated, and since there's a lot less information that was given, so the degree of freedom analysis have to be carried out to determine whether the information is enough to solve the total total problem, the overall problem. So it involves the number of unknowns and the number of independent equation. Like on the previous example is the equation, we can use up to 3 equation, and we only have 2 unknown, which is m1 and m2. So basically we can use 2 balances to solve the equation. And let's go back to the lecture notes. And so the number of degree of freedom is equal to the number of unknowns minus the number of independence equations. There you go. And in the previous problems, we have 2 unknowns and 2 independence equation. So in total, the number of degree of freedom is 0. So we state the problem can be solved. So if the number of degree of freedom is less than 0 or more than 0, the problem cannot be solved. So this situation is as a backup system or the initial step to determine whether this system can be solved or not. Or sometimes you have the number of degree of freedom is non-zero, so you still have to partially solve the equation in order to obtain some results. So yeah, so for degree of freedom analysis is quite important for large scale situation, because if you have done all the equation beforehand and all the conversion, and then you find out you couldn't solve the equation, that's pretty much disappointing. But somehow you have to solve it partially not in exam, probably in when you're working in industry or working on a research, you still have to solve some problem at least. Anyway, let's go to the next is the so this is more to an SOP or standard operating procedure to solve a single unit process material balance calculation. So this is basically a step by step on how to solve a material balance calculation. The first is, like I showed you before, is to choose a basis of calculation as an amount of flow rate as one of the streams. So you have to set the general rule on what's the basis, either is a continuous or a batch process. Then you have to decide whether it is a mole or kilomole or mole per liter or kilogram per liter. And then you draw a flowchart and fill all known variables values. Then you label the unknown variables, such as what's the mass flow rate of the incoming water, what's the outflow rate, and sometimes they give you the accumulate. And then the third one is express what's the problem statement asks in terms of label variables. And then so this is what I said before: convert all quantities to one basis, mass or mole. Sometimes they give you to kilomole, but the basis is in mole, so you have to convert it to avoid miscalculation. And the fifth one is, this is what I said before, do the degree of freedom analysis. So after you do this, you do a degree of freedom analysis in order to know whether the situation can be solved or not. So and next is write the equation in an efficient order. Start with the equation that involves the fewest unknown variables. That's in the equation. Sometimes you can get up to 3 variables that is unknown, and while the other equation, some equation already solve itself, so you have to practice on that. And yeah, the seventh one is solve the equations. And yeah, you have to do multiple equation, multiple solves, what they call it, I can't remember, but yeah, solve the equation. And if necessary, scale the process to obtain the final result. So you can scale down the process, or you can scale up the process to obtain the final result. Sometimes mostly in research, you do in experimental stage, then you have to scale up or scale down. Or if you do in industry, you can scale down to experimental lab situation. Yep, I guess that's the SOP for this one, and I think we will go for some examples for you to understand more. Alright. So we've covered the general procedure for single unit process material balance calculation, and now let's just do an example. So this is example 4.3-5 on page 102. So the first in the general procedure, the first is we have to choose the basis. So from here, the basis is 200 liter per hour. So just write it here. The basis is not 200, 2000 liters per hour. And yeah, and then we have to draw and label the flowchart. Let me just resize this. And so that's first. Second is flowchart. Flow chart. And it says here liquid mixture containing 45% benzene and 55% toluene by mass is fed to distillation column. Well, let's keep the reading and just draw the flowchart. So let's say here, that's the center of the flowchart, and feed. So that's the feed, and it's the basis of 2000 liter per hour, and the mixture containing 45% benzene and 55% toluene by mass. So this is the mass fraction. So the mass fraction, we can write it down here. So it's 0.45 kg benzene per kilogram of feed, and the toluene is 55%, so 0.55 kilogram of toluene per kilogram. And what else? A product stream leaving the product of the column, or so-called the overhead product, contains 95 mole percent of B. So, well, that's mole. So the overhead product, give me a bit longer. So the overhead product, so that's the feed, this is the overhead product, containing, so that's the mole fraction. So it contains 0.95 mole B over a mole of a product. while the rest is toluene, 0.05 mole of toluene per mole of overhead product. So we can convert this to mass fraction, which is we can just write it. I just copied it from the book. So it says here YB2. Since this is 1, 2, and the bottom one is 3. So that's YB2, and we can write it of kg of B per kg of overhead product. Well, the other one is, since there's only two product here, so the total mass fraction is 1. So 1 minus YB2, and the value is for kilogram of toluene per kilogram of overhead product. And then what else? And it says a bottom product stream contains 8% of benzene feed to the column, meaning that 92% of the benzene leaves with the overhead product. So how should we write it here? So we just follow the book. It says MB3. So since this is a mass flow rate, so there's a dot here representing mass flow rate. So mass flow rate is kg of B per kg of bottom product. To write here, bottom product T. And then for benzene, it says that 8% of it, 8% of B in feed. So that means from here, the total here, 92% went to the overhead product, while the rest, the 8% went to the bottom product. So you can find also the mass flow rate of toluene. So that's kgt per kg. So for the total, the mass flow rate, we can write this M1. So that's, since it's a flow rate, M dot, so that's, we can consider kilogram per hour. Yep. And the overhead product, since we use 2 here, so we can use M2, M dot 2. So still the same, kilogram per hour. And this one is M3, M dot 3. So still kilogram per hour. Yep, so that's our flow chart, and then now next we move to what else? Write an expression. And the question for this example is, let me change this first, is determine the mass flow rate of the overhead product stream and the mass flow rate and composition mass fraction of the bottom product stream. So here they want the M, the mass flow rate of the overhead product stream. So they want the M2 here, and the mass flow rate of the bottom product stream, which is M3. And the final one is composition, which is the mass fraction. So they want the mass fraction of the bottom product stream. So let's just go here. Oops, a bit more. So what they want here is the mass, the M3. So the M3 here, M3.3 is equal to mass flow rate of benzene in 3 plus mass flow rate of toluene in 3. So that's the M3. While the mass fraction, since you know in chapter 1 the mass fraction is the mass of the interested compound over the total mass of the product. So for, let's use the benzene, the mass fraction of the benzene here, we use xb, which is equal to the mass of benzene in the bottom product, which is mb3 over the total mass flow rate, which is the m3. Well, the mass fraction of toluene in the bottom product is, well, how should I do this? Since the overall is 1, so 1 minus xb is equal to x t3. Oh, so this is t3. Alright. Before that, I have to do a correction about, so normally the flow rate, normally we use x is for mass flow rate, while y is for mole fraction, and x is for mass fraction. So here clearly there's a mistake. So instead of y, it's supposed to be an x. So it's supposed to be x b2 minus 1 minus x b2, because this is in kilogram per kg. So that is a mass fraction, while y is the mole fraction. If you want the mole fraction here, you can, this is y already. Alright, so we move to the next part. Okay, next we have to convert the mole into kilogram, because we have to standardize everything. So since everything is in kilogram, in mass, so we have to convert this to mass first to standardize it. So that's the fourth procedure. So how to convert the mole fraction to mass fraction? So first is we just assume this part, and let's say we have we use a basis of 100 kilomole. So basis, like overhead basis is 100 kilomole. So if 100 kilomoles of overhead product goes here, so it's basically 95 mole of benzene and 5 mole of toluene. So since we know the molar weight of benzene, which is 78.11 kilogram per kilomole, while for toluene is 92.13 kilogram per kilomole. You can look this in table 1 in the textbook. So to get the mass here is easy as peanuts. So 95, so that's 95 kilomole and 5 kilomole, since the basis is 100 kilomole. So 95 kilomole times 78.11 kilogram per kilomole. So that's cancelled out, and we get, what's the value? 7420 kilogram. The next is 5 kilomole of toluene times 92.13 kilogram per kilomole. So same old, you get 461 kilogram of toluene, while this one is benzene. Alright, next. So for 100 kilomole basis, the total mass is 7881 kg, and then we have to convert this to mass fraction. So mass fraction is the mass of subject of interest over the total mass. So the mass of XB2 that we discussed before is, what's that? So X benzene is 7420 kg, so 7420 over the 7881. So in the end, the mass fraction of benzene in the overhead product is 0.942 of B per kg, while for the X toluene 2 is 1 minus XB2. So 1 minus this, you get the value. So you can write this in here. So the value is 0.942, and this one is 1 minus 0.942. Alright. And next is we can perform the degree of freedom analysis, and I can do it. Just do it here. Alright, what number is this? So the fifth step, which is performing degree of freedom analysis, DOF. So now we have unknown. How many unknown? Let's calculate it again. So we have M1, M2, and then what else? And then M3, which is MB3 and MT3, because from this M3 is MB3 and MT3, so we just find these two and we can get that one, so that's solvable. So it depends on MB3 and MT3. So we have 1, 2, 3, and 4, and we just solved this just beforehand. So for unknown, correct this first. For unknown, we have 4, which is M1, M2, MB3, and MT3. So material balance, we have 2 molecular species, which is benzene and toluene, is it? I'm not sure, I forgot. Anyway, so we have 2 material balances, since we have 2 molecular species. And then we have density relationship, which is to convert liters to kilogram. We have this, it shows it here. Where is it? And the specific gravity of the feed mixture is 0.872. So down. So we have 1 density relationship, which is the specific gravity of 0.872. And the last one is we have the benzene split of 92% goes to the top, and the last 8 went to the bottom. So we have 1 benzene split. So minus this, all of it, and then in the end you get 0 degree of freedom. So hence, this problem is solvable. Yep, easy as that. And now the hard part is how the hell we solve this problem. And let's go down and make a new point. Right. So for the next part is the solution procedure, which is number 6. Solution procedure. So the first procedure, since we've done the degree of freedom analysis before, we can use it from that. As for example, we can use the density relationship because from the graph, from the flow chart, it was given liter per hour, and we can convert it to m1. So from liter per hour, we can convert it to kilogram per hour. So let's use, so the solution procedure part A is volumetric flow rate conversion. And then, since the specific gravity is 0.872 kilogram per liter, so we can use that to find the M1. So the mass flow rate is, it was given the volumetric flow rate, which is 2000 liter per hour, and then we can use it with the specific gravity, which is 0.872 kilogram per liter. So in the end you get 1744 kilogram per hour. So that's M1 solved. And then next, using the degree of freedom, we can use the benzene split fraction, and hence to utilize that, let's use B, so benzene split. So it says like 8% of the benzene went to the bottom product. So benzene is MB3. So we can find flow rate, mass flow rate of B3. So MB3, so this is the flow rate, is 8% is 0.08 times what's the value of M1, since the benzene in M1 is 45% of the total M1, so the equation will be 0.45, which is 45% of M1, and we just found out the M1 to be 1744, so just put it in here, and then you get 62.784 kilogram per hour of benzene in bottom product. So you get M1 and you get M3 now. And next, we can use the final equation, which is the, let's look at the, you can use two material balances with the molecule species. So hence we can use, for C, we can use benzene balance and toluene balance. So benzene balance from so this is the total balance of the whole system. So let me show you to you. So the benzene balance throughout this system. So what comes in and what comes out. So let's use the benzene balance first. There we go. And so benzene balance, what goes in is 45% of M1, which is equal to what comes out from the top product and times the mass fraction X B2 of the top product plus the mass fraction of the bottom product, which is MB3. And while for toluene balance is 55% of M1, which is equal to, since this is XB2, so since there's only two compounds, so 1 minus XB2, what's left from XB2 is toluene, and times M2, which is the toluene in the top product, and the excess toluene, the overall toluene in the bottom product. So MT3. So for benzene balance, let's use the benzene balance first. Since we found the M1, we already found the M1, and what else we found it? Did we find the M2? No. We know the XB2 from the earlier version, earlier iteration, and MB3 we just found out just now. So I guess we can find the M2. So what's how to do it? So 0.45 times 1744 equal to M2 times, what's the value of the XB2 we calculated before, so the value is 0.942, which is the mass fraction of benzene in the system, in the top product. So 0.942 plus MB3 is, we found it before, is 62.784. So in the end, M2 value is 766.5 kilogram per hour. Yep, so that's M2, mass flow rate of the top product. And next is, we can do the toluene balance. So same thing, 0.55 times 1744 equal to M2. We just found out the M2, isn't it? Oops. No, we haven't found out the M2. Uh-oh, we found out the M2. What's went wrong here? Oh, no. Here, 0. No, we're using this one. I look at the wrong equation. Oh my lord. So 1 minus 0.942, because this is XB2, times M2. We just found out the M2, so 766.5 plus MT3. Yep. So solving the equation, the MT3 value is 914.7 kilogram per hour. So that's MT3. So yeah, I think we found out everything. So So M1 is 17, not 17, what's the value? 1744 kilogram per hour, and is M2 is 766 kilogram per hour. While MB3, what's the value of MB3 just now? Value of MB3 is 62.784 kg per hour, and MT3, the final one, is 914.7 kilogram per hour. Sharp. Alright. So then we can solve the final question. Alright, so the question wants, what's the question again? Determine the mass flow rate of the overhead product stream and the mass flow rate and composition mass fraction of the bottom product stream. So mass flow rate of the overhead product stream is M2, we found it, which is 766, and the mass flow rate and composition of the bottom product, so this is the bottom product, so they want the M3 and the X value, the XB and 1 minus XB, XB3, so this is XB3. So, well, let's calculate it. So M3 is equal to MB3 plus MT3. So what's the value of MB3? So MB3 is 62.8 plus 914.7 kilogram per hour. So in total, M3 is 977.5 kilogram per hour. This value is yeah, that's correct. So that's MT3. Yep. That's good. And now is to find the mass, mass fraction. So XB3. So X is for mass, while Y is for mole fraction. I think the book is wrong, I don't know, but I always use X, correct me if I'm wrong. So XB3 is equal to mass flow rate of benzene in the bottom product over the total mass flow rate of the bottom product. So 62.8 kilogram per hour, of course, and over the total is 977.5 kilogram per hour. So in the end is 0.064. Well, that's for XB3, and XT3 is, since there's two compound only, so the total is 1 minus 0.064, and you get 0.936. So yeah, that's all for this example. Alright.